Trellis-Coded modulation in xDSL. In xDSL technology, Trellis-Coded modulation, TCM, is a sophisticated forward error correction, FEC, technique that integrates coding and modulation into a single process. Unlike traditional methods where an error-correcting code is tacked on before modulation, TCM treats the selection of signal points, constellations, and the coding of bits as one integrated step to maximize noise immunity without requiring extra bandwidth. The core principle, free gain in a band-limited channel like a copper telephone wire. You cannot simply increase the data rate by speeding up the pulses, symbol rate, because the wire won't handle the higher frequencies. You also can't easily add parity bits, overhead, without slowing down the effective data rate. TCM solves this by, 1. Expanding the constellation. If you want to send 2 bits per symbol, normally 4 QAM, TCM uses an 8-point constellation, 8 QAM, instead. 2. Using the extra points for coding. The extra bits provided by the larger constellation are used by a convolutional encoder. 3. Maximizing Euclidean distance. Instead of focusing on Hamming distance, how many bits are different, TCM focuses on Euclidean distance, the physical distance between points on a signal map. How it is applied in xDSL. In modern xDSL, ADSL2+, VDSL2, TCM is applied within the discrete multitone, DMT, framework. Per bin coding, since DMT divides the wire's bandwidth into hundreds of sub-channels, bins, TCM can be applied to each bin. Set partitioning. Under BOX mapping, the constellation points in each bin are divided into subsets. 4. The encoder ensures that the most likely sequences of symbols sent over time are those that are physically furthest apart on the constellation map. This makes it much harder for noise to nudge a signal into a different valid path. Viterbi decoding. At the receiver, the MSAN or the user's modem, a Viterbi decoder is used. Instead of looking at one symbol at a time, it looks at a sequence of symbols to determine the most likely path the transmitter took through the trellis. Pros and cons of TCM in xDSL. Feature advantage/disadvantage. Spectral Pro provides coding gain, typically 3 to 6 dB, without increasing the required efficiency bandwidth. Noise Pro, excellent at handling the Gaussian noise and crosstalk found on immunity copper lines. Con, because the Viterbi decoder must look at a sequence of symbols to latency make a decision, it introduces a small amount of processing delay. Con, requires significantly more computational power in the DSLAM and complexity modem chips compared to uncoded QAM. TCM and the dual bitmap. The Japan case. One unique application of TCM in the DSL world occurs in environments with TCM-ISDN interference, common in Japan. Because ISDN lines there use a specific timed burst, time compression multiplexing, they create noisy and quiet periods for nearby DSL lines. xDSL systems use TCM-aware synchronization to switch between 2 different bit loading maps, dual bit maps, to perfectly time their transmissions with the quiet periods of the interfering ISDN line. Which flavors of xDSLs using TCM? While Trellis-Coded modulation, TCM, is a sophisticated feature, it is not present in every type of DSL. It was introduced as DSL evolved to handle more hostile copper environments where simple error correction wasn't enough to maintain high speeds. In the xDSL family, TCM is primarily found in the DMT-based, discrete multitone, flavors. 1. ADSL, G.992.1, and ADSL2+, G.992.5. TCM is a core component of the ADSL standards. Usage. It is used to provide a coding gain of approximately 3 to 6 dB. In practical terms, this allows the signal to travel further or carry more data over the same distance compared to non-TCM signals. Implementation. It works alongside Reed-Solomon coding. While Reed-Solomon handles bursty noise, like a light switch flipping, TCM handles the constant background noise, white noise, on the line. 2. VDSL2, G.993.2. As the successor to ADSL, VDSL2 uses much higher frequencies, up to 35 MHz, which are even more sensitive to noise. Usage. TCM is mandatory in VDSL2 to ensure stability at high bit rates. The Japan flavor, Annex C. A specific version of VDSL/ADSL uses a unique TCM-ISDN synchronization. This isn't just the modulation itself, but a timing mechanism to avoid interference from Japanese ISDN lines that use time compression multiplexing. 3. G.Fast, G.9701, the newest member of the xDSL family, G.Fast, aims for speeds up to 1 Gbps over very short copper loops. Usage. G.Fast uses a very high-order TCM, up to 4096 QAM. At these speeds, even the tiniest amount of noise can cause errors, so the path-based logic of TCM is critical for maintaining a 10 superscript 1-bit error rate. 4. HDSL2 and HDSL4. Unlike the original HDSL, which used 2B1Q, HDSL2 was designed to be more spectrum-friendly and reach-efficient. Usage. It uses OPTIS, overlap PAM transmission with interlocking spectra, which incorporates TCM. This allowed xDSL2 to provide T1 speeds over a single copper pair, whereas the older 2B1Q version required 2 pairs. Summary table: xDSL flavors and TCM DSL flavor uses TCM. Primary benefit: xDSL, original, no use 2B1Q, simple voltage levels. ADSL/ADSL2 plus yes, increased reach and better noise margin, 3 to 6 dB gain. VDSL2 yes, stability at high frequencies and crosstalk resistance. G.fast yes, essential for ultra-high QAM levels, up to 4096 QAM. SHDSL yes, uses TCPAM, Trellis-Coded pulse amplitude modulation. Why some flavors don't use it: early versions of DSL, like original xDSL or iDSL, utilized simpler line codes like 2B1Q. These systems were brute force, they used high voltage and low complexity. As the industry moved toward DMT to pack more data into the spectrum, TCM became a necessary partner to keep those dense data bins from being corrupted by noise. DMT, discrete multitone, DMT, is the digital modulation standard for almost all modern xDSL services, including ADSL, VDSL2, and G.fast. It is a specific application of OFDM, orthogonal frequency division multiplexing, optimized for the unique challenges of copper telephone lines. How DMT works: the bins concept: instead of sending data as a single, high-speed stream across the entire wire, which would be easily disrupted by noise, DMT breaks the frequency spectrum into hundreds of small, independent subchannels called bins or tones. Bin width: in ADSL and VDSL2, each bin is exactly 4.3125 kHz wide. Number of bins: *ADSL, uses 256 bins, up to 1.1 MHz. VDSL2, can use up to 4096 bins, up to 35 MHz. Parallel processing: each bin functions like a separate, low-speed modem. The incoming data is sliced up, and different pieces are sent simultaneously across these parallel bins. Adaptive bit loading: the intelligence of DMT lies in its ability to assess the quality of each individual bin. This process is called bit loading. 1 SNR probing: during the initial handshake between your modem and the MSAN, the system measures the signal-to-noise ratio, SNR, for every bin. 2 allocation: clean bins: if a frequency is clear, DMT packs it with up to 15 bits per symbol using high-order QAM, quadrature amplitude modulation. Noisy bins: if a frequency has interference, example from an AM radio station, DMT may only put 2 bits there or disable the bin entirely. 3 dynamic updates: bit swapping: if conditions change, example someone turns on a noisy vacuum cleaner near the phone line, the modem can swap bits from a newly noisy bin to a cleaner one in real time without dropping the connection. DMT architecture: the math behind the signal. DMT relies on high-speed digital signal processing, DSP, to handle thousands of frequencies at once. FFT/IFFT, the transmitter uses an inverse fast Fourier transform, IFFT, to combine all the individual bit-loaded bins into one complex signal to be sent over the wire. The receiver uses a fast Fourier transform, FFT, to pull them back apart. Cyclic prefix, CP, to prevent intersymbol interference, ISI, caused by signal echoes on the copper line. DMT inserts a small buffer of data at the start of each symbol. Why DMT is superior to single carrier, CAP/QAM, before DMT was standardized, a method called CAP, carrierless amplitude phase, was used. DMT won the line code wars for several reasons: feature DMT, multi-carrier, CAP, single carrier, noise surgical, turns off only the affected brute force, a single noise source can handling frequencies. Crash the whole link. Excellent, adjusts to signal loss at high limited, struggles on long or low reach frequencies over long distances. Quality copper loop software defined, can change hardware defined, requires specific flexibility frequency plans, Annex A/B, easily. Analog filters for different regions. DMT frequency layout, example, ADSL, in a typical ADSL deployment, the 256 bins are allocated to keep voice and data separate, bins 0 to 5, reserved for voice, POTS, 0 to 25 kHz. Bins 6 to 31, reserved for upstream data. Bins 32 to 255, reserved for downstream data. Summary of DMT. To summarize, discrete multitone, DMT, is the brain of modern DSL technology. Its success lies in its ability to treat a single copper wire as if it were hundreds of independent, narrowband communication channels. Here are the key features that define DMT. 1. Multi-carrier modulation. Instead of sending one high-speed signal, DMT divides the available frequency spectrum into many small subchannels called bins or tones. Each bin is 4.3125 kHz wide, in ADSL/VDSL2. Each bin is modulated independently using QAM, quadrature amplitude modulation. 2. Adaptive bit loading. This is the most critical feature for performance. DMT modems probe the line during startup to check the signal-to-noise ratio, SNR, of every single bin. Optimization: high-quality bins carry more bits, up to 15 bits/symbol, while noisy bins carry fewer or none. Efficiency: this allows the system to maximize the total throughput based on the unique physical condition of that specific copper loop. 3. Bit swapping, dynamic adaptation. DMT can adapt to changing line conditions in real time without dropping the connection. 5. If a specific frequency suddenly becomes noisy, example due to a nearby appliance, the modem can swap the data bits from the degraded bin to a cleaner bin. 4. Resistance to narrowband interference. Because DMT uses many narrow bins, it is highly resilient to RF ingress, like AM radio signals leaking into the wire. While a single carrier system, like CAP, might fail entirely if one frequency is blocked, DMT simply notches out, turns off, the affected bins and continues operating on the rest of the spectrum. 5. Efficient use of FFT/IFFT. DMT relies on digital mathematics rather than expensive analog filters. Transmitter uses inverse fast Fourier transform, IFFT, to combine all subcarriers into one time domain signal. 6. Receiver uses fast Fourier transform, FFT, to separate the frequencies back into data bits. This makes the hardware highly scalable and cost-effective. 6. Guard intervals, cyclic prefix, to combat intersymbol interference, ISI, caused by signal reflections on long copper wires. DMT inserts a cyclic prefix at the beginning of each symbol. 8. This acts as a buffer zone, ensuring that delayed echoes of the previous symbol do not corrupt the current one. Summary table: DMT at a glance. Feature function benefit: divides spectrum into 4.3125, prevents total signal loss from localized subchannelization. Kilohertz bins. Noise: assigns bits based on SNR per, achieves the theoretical maximum bit loading. Bin speed of the wire: moves bits between bins. Bit swapping increases connection stability during operation. Adds a time buffer between, eliminates errors caused by signal cyclic prefix symbols. Echoes: multipath.